and also all the participants for the 5 days international FTP on 5G, IoT and artificial intelligence research trends and applications, organized by Department of Electronics and Communication Engineering in association with IEEE Bangalore section ITS chapter, IET Bangalore section and IEEE Atria student branch. And I would like to introduce our today's speaker, Dr. Akash Gupta sir. Dr. Akash Gupta, member of IEEE, received a BTech degree in Electronics and Communication Engineering from UPTU Lucknow, India in 2009, MTech degree in Communication Technology from University of Allahabad in 2011, and PhD degree in Electronics and Communication Engineering from University of Delhi, New Delhi. He works as an assistant professor with the EC department, LMN Institute of Information Technology, Jaipur, India. His research interest includes next generation wireless communication, visible light communication, and cooperative communication. He has published more than 15 research papers in international journals of high repute like IEEE Transactions of Broadcasting, IEEE Wireless Communication Letter, and IEEE System Journal. He has been technical program committee member for several major IEEE conferences. With this introduction, I'll welcome Akash Gupta sir for this session, and over to you, sir.
Thank you, ma'am, for a warm welcome. Okay, so can I start?
Yes,
and
sir.
I'm thanking the Department of Atria, Easy Department Atria, for this invitation and for such a knowledgeable guest, knowledgeable meet for this 5 days that is starting from, I think, 20. It was started from 25th, right, ma'am? From 27th onwards to 31. Still first. Okay, so I will be giving my screen is visible to all, right?
Yes, sir. It's visible. Yes, sir.
Okay, so let's start with the presentation. So I am here to give a brief introduction about how our wireless communication will be changing the stream of wireless communication. So machine learning and wireless communication amalgamation will be bringing a new change and bringing a new generation in wireless communication, and that will be a part of beyond 5G or 6G communication. We have a good talk yesterday regarding 6G, what were its requirement and how it will be changing our world altogether, because from 5G onwards we are not talking about people-to-people communication. We are talking about D2D communication, M2M communication. We are talking about IoTs, edge computing and everything. So now our generation of communication is completely changed. We are not even concerned about the data rates. We are concerned about the energy efficiency, energy constraints, because now the devices are low powered. So yes, this presentation will be completely how machine learning will be changing the generation of our communication. Fine. Okay, so if I talk about future wireless generation communication, that can be including 5G, because we have not seen 5G till now. It is in the deployment stage, and most probably by 2022 we will be having the first experience of 5G. Reliance is giving us millimeter wave. Okay, so how it will be, because now the communication is not even only constrained to this people-to-people communication or from base station to user communication. It will be completely different. Vehicles will be connected, UAVs will be there, okay, and buildings to building communication will be there using FSO. Now each sensor or each device that can be turned on or off, that can be switched on or off, that will be connected to the server. That means our complete generation of seeing things around us will be changed. Everything can be controlled now. So if everything can be controlled, then we need a backbone of communication network that can support this. Okay, so what is future generation communication? In this diagram, it is clearly seen. A beautiful diagram given by Goldsmith and Regression professor. So in this, it can be clearly seen that UAVs are connected to each other, whereas UAVs are connected to base stations or the terraces of the buildings. Even in the buildings, the different offices are connected to each other. Fine. So local area networks will be there. Okay. And then there will be different hetero cells available. That means there will be micro cells, femto cells, atto cells. Okay. Then if you talk about the vehicles, the complete scenario in the automation will be changing because now the cars will be self-driving cars, automated cars will be available. Fine. And these cars will not be connected to each other, but it will be connected to everything. That means they will get the maps updated, or they can get a location updated based on the data that they acquire. So they are acquiring as well as transferring the data to the server. Okay, so next generation communication, we are talking about high data rates, low latency, high reliability, low power, and everything. So we are talking about autonomous cars, smart cities, the body area networks. Now we are talking about sensors that will be mounted in or out of our body, and that will be tracking our different organs. Let's say a person suffers from a heart attack, sudden heart attack is there. So the sensors will track its heartbeat, and before anyone can react, the sensors will be calling SOS, and so that the patient can get the medical facility on time and his or her life can be saved. Fine. So body area network will be a big task and big area on which further research will be based on. Similarly, Internet of Things, anything that can be switched on off, this is a part of Internet of Things. That means through internet, we will be controlling them, we will be gathering information through them, and everything will be now under the control using a simple press of keys, or what you can say, using remote accessing everything from our office. Even our home will be under our control when we are sitting in our office chairs. Fine. So now the complete scenario is changing. Now, so we require a move on from the traditional way of thinking to a adaptable system. So adaptive system that can help us adapt to the changing conditions. Fine. Okay, so now we want ubiquitous communication between people and devices. Fine. Okay, so what are the enablers for increasing data rates and performance in 5G? Now, we are not even concerned about data rates. Now, data rate is not an important design paradigm in beyond 5G communication. The thing that we will be talking about, the metric that we will be talking about is quality of service. That means what quality of service that we are providing to the end user. And this quality of service support will be differentiated and will be of different types, because suppose if I'm talking about quality of service of a robotic control application, something related to robotics, okay, and a person who is wanting a music application using snipping applications, their demands is different, because for robotic communication you want low latency and high reliability. You require low latency and high reliability, because if there is a lag between the command sent and the execution of the robotic control, then it can cause a big problem. Whereas in terms of music streaming applications, the latency is not a big task. What we want is high data rate, or average data rate that can stream music without buffering. Okay, so now the quality of service at the end user is a big concern for us. Fine. So if we talk about the enablers that is providing increasing data rates, first of all is that we are started searching for different spectrums. One of the reasons of low data rate provided by the 4G and the 3G, okay, was the spectrum scarcity. The number of users was increasing exponentially, but the spectrum was limited. So there was a spectrum scarcity faced by the telecommunication union from the last decade. Okay, so now what we have started searching for is different or unlicensed spectrums. More spectrums is required, and we have moved into millimeter wave, terahertz communication, and so on. Even in optical wireless communication, we have explored a great capability of deploying optical wireless communication in indoor scenario as well as in outdoor scenario. So if we talk about indoor optical wireless communication, we are talking about visible light communication, that is using the lighting infrastructure available in our home for communication purpose. And if you are talking about FSOs, that is free space optics for backhaul links, then it is also a technique or a medium or in which optical carriers are being used to transfer data from one building to another or one curb to a home. Okay, so all of these are unlicensed spectrum. We don't require bodies to govern it, so that can be used without taking any license from the authorities. Okay, so we can deploy FSOs and PLC at our home without taking any without paying anything for the spectrum. Similarly, for the higher data rates, we have moved into massive MIMO, that is providing higher data rates. Then what we have done is we have restructured our cellular system design that was consistent from 2G, 3G, and even 4G. Now we have moved into heteronets, that is heterogeneous networks. We have moved into smaller cells. Okay, and these smaller cells will be a part of a bigger cell, and so on. Okay, so there will be heterogeneous networks of cell that is available, and there will be handoffs between each other. Then we are talking about software-defined wireless networking, and that will be in which there is a capability to change the algorithm according to our need, according to the changing environment and everything. Further, now what we have been thinking about is finding new physical layer techniques. Now, everything, because if we are talking about adaptabilities and everything, so we have to search new techniques so that the physical layer can be improved further. So first is new waveforms. So there are possibilities of orthogonal time, frequency, space modulation that is robust to the changing environment, that is robust to the channels that the normal waveforms cannot adapt to. Okay, so there is OTFSM. So there is a waveform that is orthogonal time, frequency, space modulation, and this is very robust to changing channels that can to which our signal or our waveform can adapt to. Then there is new detection techniques. Now we are talking about IoT devices. So IoT devices are having a constant of signal processing, because we cannot go for very heavy signal processing applications in the IoT devices. Similarly, they are they have energy constraints. Okay, so now what we have to think about is we have to think about new detection techniques that can be a little light on the computational end. That means they require less computational complexities. Okay, then we have moved into new coding and decoding mechanisms. So now the coding and decoding mechanisms are more adaptive, and the code length may be changing based on the system or the channel conditions. And further, we have seen that because the number of users are increasing day by day, so the orthogonal schemes that were available for multiple access, that is OMA was available, orthogonal multiple access schemes were available, and it was not sufficient to cater the requirements of high increasing user strength. Okay, so now we have to switch over to more to a non-orthogonal multiple access technique, more innovative techniques in which they will be divided, or they will be allotted. They can be bifurcated based on the power allotment. Okay, so they can exist in the same spectrum as well as on the same time instant, but the power, they will be provided superimposed codes and their recoding will be performed based on that. So NOMAD technique is available and is a part of our 5G communication system. Okay, so non-orthogonal multiple access. So everything is in the physical layer techniques. Now, so if we are improving that, we are improving the data rates as well as the reliability and the latencies. So when we have figured out what we want, now comes challenges. What are the challenges, research challenges of beyond 5G or 6G communication? What we want was that everything should be adaptable. We should make more accurate systems. We should provide more reliability. We should provide less latency and everything. We want the best. The quality of support, quality of service should be the best. Fine. So the challenges that is there for the beyond 5G and 6G communication is first connecting intelligence. That means there must be a framework that can support a real-time trustworthy control. Because if we are implementing AI and ML on the end user systems or even in the network, then what we want is that these computational facilities be provided with real-time data so that their efficiency can be improved and the quality of service experience can be improved. Okay, so we want that this intelligence system can be connected, fully connected. Then second is network of networks. That means the beyond 5G or 6G communication system should aggregate multiple type of resources. Okay, that means I can say that communication data, AI processing, all the different scales ranging from in-body, intra-body, intra-machines, indoor, data centers, and everything should be connected. And all of these will be a network of networks because inside there will be a network. Body area network is another network, then local area networks, MAN, WAN, all these networks will be a part of our beyond 5G communication. So heterogeneity will be required, will be a part of beyond 5G communication, and these deployment will be massive. Okay, because we are talking about trillions and trillions of IoT devices. So what we want is there must be a communication network that can serve this purpose, that can connect all these nodes, and there must be a reliable connectivity between these devices. Further, if I talk about the third point, that is sustainability. Now, everything is connected, but everything is energy hungry. And if I talk about small devices, small sensors, they are always low on power requirements. Okay, so they are always low in power available at their nodes. Okay, so energy constant is very much at their end. So what we want is the energy should be optimized in this digital infrastructure that we are wanting to create. Okay, and this will revise the full resource change of mobile networks. That means everything, every network will be now optimized according to the needs. That means energy efficiency should be there. Now, and lastly, if I talk about the extreme experience, that means the bitrate should be extreme, latency should be minimum, as minimum it can be, considering to be a real time. Okay, then infinite capacity should be there, localization can be supported. Okay, and so we want the extreme experience. VRs, ARs can be supported. Okay, so this is what beyond 5G or 6G is to be made. All these challenges has to be met if we want to prepare a system beyond 5G. So what is the role in beyond 5G or 6G communication? So if we are talking about ML application, that is machine learning application in our communication system, it will be definitely different for different layers. When we are talking about physical layer, we are talking about replacing the mathematical models with ML. Still, at till 5G also, we are able to analyze our communication system, check the feasibility, and generate new systems, okay, using mathematical models that is available with us traditionally. But what happens is, using these mathematical models, it is very difficult for us to model nonlinearities. And even if we are modeling the nonlinearities, the computational complexity increases many folds. And the time needed to execute such signal processing algorithms will be far more as compared to if we replace these mathematical models using ML. Fine. So one of the requirement was to replace the mathematical models. Second was that till now what we do is in communication we break the complete chain from transmitter to receiver into multiple blocks, and each block is optimized independently from the other block. That means if suppose I want to break my system into different parts, then there will be modulators, demodulators, source encoders and source decoders, similarly channel encoders and channel decoders. When we talk about source encoder, it tries to reduce the redundancy by making variable encoding. Okay, that means the characters or the symbols that are repeated more frequently are provided less bit, whereas the symbols that are repeated less frequently are provided more number of bits. Fine. So we try to reduce the redundancy in the source encoding, but using the channel encoding we increase the channel redundancy to to provide the signal error correction and detection capabilities. Fine. So one is adding redundancy and another is reducing redundancy. So if we try to optimize them individually, the complete system may or may not be optimal system. So what we want is that the complete system should be treated as end-to-end system and it should be optimized as a whole. So that will be providing us the optimal service that we want. So deep learning is one of the important or efficient tool when that can be applied in physical layer. Okay, so what we do is we use autoencoders for end-to-end modeling. In the map layer, we are talking about resource allocations. That these resource allocations can be energy resource allocation, channel allocations, and so on. So reinforcement learning provide us a tool for autonomous, that is independent decision making. Right. Similarly, in the network layer, the quality of service optimization uh, can be applied. Machine learning can be applied to give quality of service optimization. Okay, because most of the problems that we solve in wireless communication are non-convex. So machine learning is an important tool that can help us to figure out that. Similarly, in the application and the transport layer, ML can be an important constituent of the transport layer, okay, to provide a desired quality of service that we want. Okay, so in the sixth generation communication, we are talking about XRs, that means extended reality, virtual reality, augmented reality, or mixed reality. We are talking about autonomous drivings. We are talking about massive robots that are connected to the servers every time. So for these things, we want machine learning integrated in our wireless communication chain. Okay, so this is what we are dreaming for and what we want to implement. And researchers have started working on this, and multiple things have been applied. Fine. So if we want to go now starting with machine learning paradigms, so if we want to bifurcate or divide our machine learning into three parts, it will be supervised learning, unsupervised learning, and reinforcement learning. Supervised learning means there is a data available, okay, for training, and based on the training that we performed with the training set, we will be testing it on the other set and checking whether the trained model is working according to our needs or not. That means the loss function is reduced and the efficiency is increased or not. When we talk about supervised learning, we are talking about mostly classification and regression. That means, let's say we are training, let's say there are two fruits, banana and oranges. Okay, so what we do is we feed our system machine learning model with different images of bananas and different images of oranges. Now, based on this testing data, what will happen is a model will be created so that it can classify the bananas into the bananas group and the oranges into the oranges group. Now, whenever we are feeding this system with a new image of a banana or an orange, it will definitely or it will accurately predict whether it is of a banana type or an orange type. Fine. So classification is one of the application of supervised learning. Similarly, a regression, that means if we have trained a system using some values, it can predict based on the input values what will be the output value. So prediction of the values is regression. I'm not going into the detail. Okay, and when we are talking about unsupervised learning, that means we are talking about the system machine learning that learns to classify the sample of the input. Okay, there are no labels, no data heads with labels and labels available. So it trains while it operates. Okay, so it will be taking the data and then it will be training itself. For example, it is used for clustering. Okay, so K means clustering in one of the algorithms of unsupervised learning. When we talk about reinforcement learning, we are talking about there will be an agent and there will be an environment. Okay, so the agent will be continuously sending what you can say input to the environment, and the environment will be giving either what we can say that positive response or negative response. I am not exactly remembering the word. So if I'm getting a positive response, that means I'm getting a positive response. I will be making the cumulative gain, or what you can say the cumulative reward. I'm getting a positive response, that means I'm getting some rewards. So the cumulative reward should be maximized in long term. So the agent's task is to maximize the rewards. Okay, and in this task of performing things and getting rewards, the system get trained. That is the reinforcement learning. Then comes the federated learning. Now what happens is in wireless communication, the privacy is very big concern. So the user terminal doesn't want to share all his data or her data to the central server. And the other reason is that we don't want to congest the server, because when we talk about wireless communication, we are talking about low latency systems. Okay, so if we talk about a system in which there is a device and there is a server. Let's say this is a device and there is a server. Okay, so if I am sending the data and getting a feedback every time, so this will take a time. Okay, and this time will be affecting the latency of the complete system. Okay, and the second reason is the privacy. So what happens is, rather than loading the model in the server, what we can do is, in the federated learning model, what happens is the mobile devices have a ML model in its own device. Okay, so that model will be trained on the data that the user will be generating. For example, a keyboard, if I talk about a Google keyboard that we are having, so it gets trained by the number of words that we are using, and the internal model will be automatically updated by whatever we are doing. It is continuously learning. And then the data from all the devices will be weighted and the cumulative average will be taken at the server, so that there is a uniformity between the devices. Okay, so if I go to the model, what happens is, if I talk about the device, each local learner trains a local version of the ML model on its own local data. That means I am generating the data and I am training my ML model by my own. Okay, so this local model parameters updates are sent to the controller. Now the controller, what we are doing is we are sending the weights that we are using, or the model train model weights, to the server or the controller. Now this controller will perform the weighted average of all the parameter updates to get a new set of parameters for global model. So the server will be preparing a global model, and this global model will be updated back to the local models. That is the user device. Okay, so in this way, even though the localized uh, data learning model is being prepared, but it is still updated by the global parameters. Fine. So in this way, we are helping our server not to get congested, as well as preventing the privacy issues of the user. So federated learning is one of the most used or a recent trend in wireless communication. There is another model of hierarchical federated learning because machine learning algorithms on our phone using high computational capabilities will be draining our battery. So rather than that, we can go for hierarchical federated learning, in which there will be different local units that will be getting trained by our data, and then their weights will be sent to the central server to get the global parameters. So there is another hierarchical federated learning model that is being implemented in wireless communication. So this is a structure of that. Okay, moving into the reinforcement learning. So reinforcement learning helps us for resource allocations and so on in wireless communication applications. So in reinforcement learning, an agent interacts with an environment and learns how to take actions. So I am a new person and I don't know how to react in this world. So what I will be doing is I will be performing things and my mentor will be observing me. So whenever I do a particular thing very correctly, I will be getting a reward. And whenever I do something wrong, I will be getting a beating. Okay, so the agent observes the state of the information environment, whatever be the environment condition, and will be taking an action. Okay, and based on the action, it will be getting a reward, and when it gets a reward, it moves to the next state. Finally, it is in the process, it is learning. The model is getting learned. Okay, so the agent aim is to maximize the long-term cumulative reward. Finally, what I want is that my reward should be maximized. Okay, so resource allocation algorithm, when we talk about resource allocation, that means spectrum allocation, energy allocation, and so on, power allocation in communication, then that can be solved using reinforcement learning. And we will be seeing some applications of that. So power control, beamforming, modulation, coding schemes, all can be solved using reinforcement learning. Next, moving to deep learning. This will solve our physical layer requirements that we were having. So deep learning model is based on the artificial neural network. Okay, so that means the ANNs that we have been using for much while. Now we will be implementing that in a physical layer to optimize a complete system. Fine. So the rise of deep learning system has mainly fueled the availability of because now the computational capabilities at our home, even the desktops that we are using are having 8 GB RAMs and 16 GB RAMs. So now the computational capabilities and the powers that we have, that has facilitated us to perform high computational algorithms, execute high computational algorithms, and make deep neural networks. Okay, so the DNNs or the deep neural networks can be feed-forward, convolutional, recurrent RNNs, that is recurrent neural networks, and can provide solutions for spectrum awareness applications ranging from channel modeling and channel estimation, and even for signal classification. So one of the applications of machine learning in wireless communication is channel estimation. When we are moving into the UAVs, the UAVs, unmanned aerial vehicles that we are talking about. The channel for that is not easily, the mathematical frameworks are not available for that, because multiple parameters are affecting its channel. The shadowing and the fadings are available, and then also there is the UAVs are not that stable, that so multiple parameters are affecting the signal quality or the channel quality. So to estimate the channel condition to get the CSI, channel state information, is a big task, and that can be performed using deep learning, or we don't require CSI. We will be taking on the data that what we can do is, because we know the data that we are generating, X is known. Okay, so we can train our system to get Y, because if X is known, then Y is also known, because if I transmit 1, I know that I will be getting 1. So in that case, what happens is, because X and Y's are known, we can train our system accordingly. Deep neural network can be trained, and the weights can be found easily, and the loss function can be minimized. So in that case, we don't require channel state information, and we can train our model accordingly, and that will be adaptable to system change in the parameters that can happen because of climatic condition, because of the sway in the UAVs and so on. Okay, then to support the fast response of spectrum changes, autoencoders are mostly used, and we will be seeing an application of deep neural network or deep learning based autoencoder system to iterate an end-to-end wireless communication system. If I talk about a simple neural network system, so what will happen is, there are n inputs or n different inputs, x1, x2, and xn. They are weighted and added. Okay, they will be weighted and then they will be added, and this addition will be now passed through an activation function to give an output. Okay, so if I talk about multiple layer, or what I can say, deep neural networks, then there will be multiple layers. So what I am trying to do is, so if I want to make a system, there will be an input, okay, and there will be an output. Okay, let's say this is a black box or a gray box. We generally call it a gray box. So we know that x naught is there and y naught. Okay, both are vectors. Fine. So this box will be a function of this x naught, and then there will be a theta, that will be the activation function. Okay, their parameter theta, any parameter theta. So now what happens is, if we are talking about multiple layers, okay, then my function of any, let's say the lth layer, will be dependent on the input of that L-1, okay, and then the activation function at that layer, that should be equivalent to, if I say, then the activation function at that layer, that is sigma L times of weighted multiplication of all XL minus 1 plus a bias BI or BL. Okay, so WL are the weights, and BI are the bias that we add. Okay, so every layer will be a function of the previous layer output, and so on. Fine. So what happens is, in this neural network, we have to divide the data into two parts: the training data and the testing data. So there will be a training data, 80% will be training data and 20% will be testing data. Multiple papers use 70-30 also. So by the 70% of the data, what we do is, we train our neural network, this network, so that our loss function can be minimized. Okay, so we know for a set of inputs and outputs that we already know the training data. We find out the loss function, because what we want, the estimated value of y cap should be equivalent to y. The estimated value of y cap should be equivalent to y. So what we want is minimized loss function between y cap and y. And in doing that, we will be finding the optimized values of weights and the biases. Okay, mostly what we do is we find the optimal values of weights. And when we have found the optimal values of weights, now we will be providing it test data. And next, what we will be checking is whether it is fulfilling a requirement or not. Because once the model has been trained, now it can be used for deployment, for applications, directly applications. Fine. So our motive will be to find the weights using the testing data, find the weights using the training data, and then implementing it on the testing data. Okay, so mostly there are different activation functions, the identity, binary step, and most of the researchers, and we are using ReLU, that is rectified linear unit. So this mathematical function is available, and we just apply it and find the optimal weights. So when we talk about multi-layer perceptrons, that means there are multiple hidden layers between the input and the output, and each hidden layer will be having its own activation functions. Okay, then what we want is, this is a fully connected neural network, because every node, input node, is being connected to the hidden layers and so on. So every neuron is connected to another neural node. Okay, so the MLP consists of input layer, output layer, and between them there will be multiple hidden layers. So now again the same motive is there. That means using the training data, we will be finding out the weights. Okay, finding out the weights of the hidden layers, and then using that trained model, we will be using it to classify the testing data into cats and dogs. So once we have given the different images, one of the crux in using in using deep learning is requirement of huge amount of data set. Okay, because the more we provide the data, the more accurate our system model will be trained, because more optimal weights can be found. Okay, so if we are providing thousands and 10,000s of images of cats and dogs in different poses, okay, from the side images, the front image, the top image, and so on, and then when we are providing it, the training data of a dog, let's take a picture of a dog, give an input to this trained model, it will be definitely predicting it between cats and dogs efficiently. Okay, so it is seen that if we increase the hidden layers to 3, the efficiency of predicting cats will be almost 99%. Okay, fine. So now coming to the applications of ML in each layers efficiently. Okay, so what we want is a complete optimized system, that is a complete end-to-end systems, and the non-linearities can be easily modeled. Okay, so that we are not going for approximate models. Now we are wanting an exact model for everything, for the non-linearities. If we think about from where we are getting these non-linearities, we are getting these non-linearities for the power amplifiers that are used at the RF ends, because every communication system will be consisting of algorithms, algorithmic section, as well as RF chains. And this RF chains will be consisting of power amplifiers that are highly non-linear in their nature. Okay, so when we talk about channel coding, so one of the requirements of a efficient channel encoding system will be that it should firstly overcome the imperfections of the channel, because the channel will be providing noise, and these noises will be creating errors. So the channel coding scheme should provide capabilities to the signal, so that it can recover the signal back from the erroneous bits that has been added. Okay, so error correction and detection capabilities must be there in a communication system. Now, when we are talking about this, after the discovery of turbo codes, okay, the long back, that was almost close to the Shannon limit. Okay, so most the new schemes were not easily developed, or we can say LDPCs were developed, polar codes were developed, and but now the codes were becoming more and more complex. The code length was increasing, and more complexity of the coding schemes were increasing. Fine. So now what we wanted was that this coding length or the code length should be adaptive to the system requirements or the channel requirements. If the channel conditions are good, that means it is not adding much errors to the signal, then we can go for a lower code length. And if the channel conditions are very bad, severe impairments are there, then we can go for higher code lengths. So channel coding should be adaptive, and that can be easily possible using deep learning embedded wireless communication system. Then coming to synchronization. So we all know that all the devices that we tackle in this real world communication system, okay, that should be synchronized with there must be synchronization in time and frequency domain. Okay, if this synchronization doesn't meet other system requirements, fine, so everything will be wrong. So it should meet the system requirements at the starting point before the communication can even start. So the accuracy of the synchronization should be maximized, or should be maximum. Fine. For this, there is a solution using a deep learning encoder, that is autoencoder, and end-to-end autoencoder can be used. Okay, and that will provide the optimal performance by guaranteeing the synchronization between the two end users. Okay, so so everything will be optimal. Next, moving to positioning. When we talk about positioning, so yes, the current system is also providing us indoor positioning systems, but that is only taking into consideration the LOS link. And when we take into the consideration non-line of sight link and LOS link, then what happens is this model that we have made, the models that we are using for indoor localization, that fails, because mostly when we model an indoor localization system, we only go for line of sight link. And mostly this line of sight link is almost consisting of 96% of the power. Okay, but to make system more accurate, we should consider the non-line of sight link also. In that cases comes our deep learning or ML based solutions. Okay, so ML based solution based on deep neural network can provide the solution. So now the inputs will not only be the receive signal strength, that is RSS. We will be now going for the user positions, and the data will be updated as the user moves and so on, and the training data will be collected by the sensors mounted on the bodies, and a complete system will be trained based on the collected data. So now we are not just going by the RSS or RSI that we usually go when we go for indoor localization. So now if we are talking about the machine learning based localization system, then if suppose we are taking a case of a VLC based indoor localization system, now what happens is, if we are using a VLC based localization system and a bulb, that is external illumination is available, that will cause an error. Okay, so the sensors must not be affected by this external illumination that is acting as a noise, and this is only possible if we provide a system with a trainable system that is adaptable to the change in the environment, and that is only possible if we implement machine learning at the positioning system. Then comes the channel estimations that we have already discussed, that the LMS, the linear minimum mean square error, that is LMMSC estimation that we were using till now, is far good when the channel is linear and stationary. It is absolutely correct and it gives fine results when the channel is linear and stationary. But in the real world, no channel is linear and stationary. Mostly they are non-linear and non-stationary because of the amplifiers and the channel change condition changes with change in the environment. Okay, and the users are moving, climatic conditions are changing, and everything is changing. Fine. So now what we want was an estimation technique that can accurately estimate the channel conditions. Okay, so now again, the deep learning based channel estimation gives us the optimized result when we want to find when we are going for the channel estimation. Okay, because they will be acquiring the data and because in wireless communication, when we are talking about, the data is synthetic. Why we are saying synthetic? Because now the data that we are generating, we know what we are generating, and we can provide the receiver with the same data. Okay, so if x and y are known, that is input and output are known, we can easily train the weights. Okay, so we don't have to collect data from other sources if we want to estimate the signals. So the pilot signals can be generated, and these pilot signals can be used to train the deep learning based communication model. And hence the channel estimation can be done efficiently as compared to LMSC that was only limited to linear and stationary channels. Then coming to beamforming, we already know that beamforming solutions can provide us low power because now the beams will be more directed towards the users, and this will provide what you can say this signals will be now less sensitive to the interferences, the coverage will be increased, and the mobile devices will be requiring less energy power, so it will be leading to reduced energy consumptions. Fine. So now what we are talking about is intelligent antennas, not a dumb and basic antennas that we were using in the. So now we can steer and beamform these antennas. Okay, so again, these beamforming can also we can implement ML in these beamforming, machine learning in this beamforming to get optimal solutions so that these beamforming can follow mobility patterns. Okay, and based on that, it can tune itself. Fine. So it will be providing coordinated beams to the neighbor base stations, provide appropriate powers to different beams according to the mobility scenario of the system. Then comes the physical optimization, as we have already discussed that the real communication systems, most of the optimization problems are non-convex. And because if I talk about some non-convex optimization problems, we can think about if we want to maximize the throughput by as a power as a constant, power control as a constant. So we want to maximize the throughput and by means of our power control. Or if we want to optimize the spectrum sensing of the cognitive radios, fine. So these are all non-convex solutions, non-convex problems, and these non-convex problems can be solved by dual decomposition techniques, but it will require high computational loads and will be requiring lots amount of time. Okay, so in this case also deep learning will be helping us to solve these problems. That means non-linear or non-convex optimization can be done with reduced complexity and computational load. Next, moving to ML, that is machine learning at MAC layer. When we talk about MAC layers, the resource allocation is mostly done because this resource allocation can be done at the other parts also. Okay, So these MAC layer will be in control of resource allocations, modulations, and different coding schemes can be also taken into this thing, and handover control will be taken into consideration. Okay, so if we talk about the federated learning for orientation and mobility prediction in wireless virtual reality networks, what we do is that from the uplink, if we talk about this virtual reality systems, okay, so that will be dependent on the user position as well as user orientations. Fine. So what we will be doing is we will be using uplink to give the feedback or give the the position or the tracking information to the server or the controller. So the uplink will be giving the tracking position, information, whereas downlink will be giving the virtual reality experience. That is, virtual image transmission will be done using the downlink. Now, because this will be requiring huge data rates, so what we will be doing is downlink will be on millimeter wave because we are talking about beyond 5G millimeter wave, whereas the uplink may be on sub 6 gigahertz band. Okay, sub 6 gigahertz band. Okay, now because we are using millimeter wave for downlink, so now the user orientation will be a big concern because it will be affected by the user body because the millimeter wave will be blocked by the user body and the user who is experiencing this virtual reality networks, okay, this virtual reality applications. So now every time based on the user position and the user orientation, the tracking information will be feedback, and based on that these millimeter wave signals will be changed. Okay, so the mobility and the orientation of this user, virtual reality user, will be proactively determined and will be updated to the controller for high virtual reality experience to the users. Then comes the predictive resource allocation in machine type communication. Okay, so when we talk about machine type communications, we are talking about devices that have low mobility or mostly stationary. Okay, so it is very easy to predict their nature, or we can easily predict the resources that they require, the power requirements and the spectrum requirements. So yes, we can and we can easily model their traffic requirements of what at which time which devices are more proactive and so on. So based on that, we can allocate the resources to different machine devices. Fine. Similarly, when we go for predictive power management, same thing can be done. That means that based on the channel conditions, we can optimize the power requirements at different terminals. Okay. And similarly, asymmetric traffic accommodation. When we talk about asymmetric traffic accommodation, we know that the wireless data traffic is asymmetric. The uplink and the downlink require different speeds of operation or data rate requirements. Okay, so if it is made more adaptable to the change in the requirements, then it can help us make more optimal systems. Okay, so yes, we can implement RL in MAC layer for making the system more and more optimal to changing conditions. Then coming to application layer, when we talk about ML-aided UAVs, for every UAV, when we talk about UAVs, first we have to control. So because if we are not controlling its flight, okay, then it cannot fulfill the requirements of communication. So when we talk about UAV control, we are talking about communication control co-design. Okay, so the real-time UAVs will be communication control co-designing will be done. So what happens is when we give the UAVs a flight, when UAVs are in the flight mode, so firstly what will they do is the manual control will be there. So in the manual control, the UAVs will be sensing its climatic conditions, whatever be the wind speed, what what are the climatic conditions, what is the thrust by the air, and so on. And it will be sending this data to the ground control. Okay. Now this ground control, based on the data that is being acquired by the sensors from the UAVs, will be creating a model. And once this model has been correctly framed or made, then this model will be sent to the UAVs, and now the UAV will move into from the manual mode to autonomous mode. That means now the system has been trained, and now UAV can fly by its own. Okay, so no manual control will be required from the ground station. When it has been done, now even for the changing climatic conditions also, the UAVs can be easily stable. And once it is stable, it can fulfill the requirements of the communication in case of some natural disasters, or even in case when a certain area of land is in the shadowed region. Okay. Similarly, when we talk about opportunistic data transfer in vehicular communication, these vehicular communications are mostly dependent on the mobilities. Okay, and what we want is that the experience of these vehicular networks should not be affected by the mobility. Okay, and what we want is that the traffic safety can be improved. Okay, so what we want is, we want this complete vehicular V2X system, V2B system to be highly efficient, and it can be trained based on the changing environment, and hence ML can be applied to these vehicular networks in which more mobility prediction and network quality estimation can be done. So this is a simple system in which if suppose a system or vehicle wants an handover, it should be predicted beforehand, so that there is no change time taken in the changeover from one cell to the another, handover from the one cell to the another. Now moving into the deep learning application of our conventional communication system, that is end-to-end system using deep learning. So till now what we are framing is that we break our system into simple modules, or lower level modules, like source as encoder, channel encoder, modulator, then channel is there, detection is then we go for detection, channel estimation is done, demodulator, channel decoder, source decoder, and so on. We send a series of data, that is 0, 1, 1, 0, and because this channel is producing some impairments, what will happen is the symbol, suppose we are using a QPSK, 0, 0, 0, 1, 1, 0, 1, 1 is being transmitted. Because of this channel conditions, what will happen is these will be, the constellation will be changed. Okay, so this will be causing some errors. Let's say 0, 1, 1, 0 was transmitted and it became 0, 1, 0, 0. Fine. So now there is a bit error rate caused. Fine. So this was the conventional system that we were using. Now what we want is, we want to replace it using DL based system. So what was the drawback? Yes, it was working according to our wish. So why we are going for DL based system design? So the first answer to this is that the imperfections and non-linearities of practical communication system was not being modeled by the system, by the mathematical framework that we are using. So, and even if we try to map them or model them, it will be highly complex systems, right? So to make the system channel state information more accurate, to make the system more accurate, we want these nonlinearities to be a part of our analysis. Then we are moving into the thing that we have already discussed, that what we do in communication system, traditional communication, we optimize each block separately, and that may give the optimal result, but that is not an optimal solution, because mostly the solution is not optimal. Okay, so rather than going for module by module optimization, we are thinking about end-to-end optimization. So we will be thinking about optimizing the complete communication system from the transmitter to the receiver. Okay. Nextly, the time requirements, that is, the learned algorithms can be executed faster and the energy requirements will be far lower as compared to the traditional communication systems. So these were the requirements, or these were the drawbacks in the traditional communication systems. That is why we are moving into a DL-based communication system. So this is the basic building blocks of a DL-based communication system that is used as an autoencoder. So now what we have done is we have taken symbol S that belongs, that means symbol S belongs to a m-dimensional space. That means m symbols are there, 1 to n, and each symbol is of k bits each. Okay. Then we have passed it through multiple hidden layers, that is, multiple dense layers are available, and each dense layers are provided with a normalization layer. This normalization layer is provided to normalize the power requirements, the power constant that is available at the transmitter and the receivers. And then at the noise layer, what we have implemented is simple adaptive wide Gaussian noise, AWGN. Okay, and our agenda is that using the data that is available, that is testing data that is available, we will be finding out the weights so that the estimated S cap should be more and more closer to S. Okay, and by making this so that estimating the loss function to be more and more optimal, okay, that means minimizing the loss function, we are finding the weights of individual layers. So yes, we have talked about this. Transmitter selects a symbol S containing k bits, k information bits, and thus k information bits will be mapped into n bits, just adding the channel encoding part. Okay, so it will be a part of it will be a real vector of n dimensions. Fine. So transmitter consists of one-dimensional convolution 1D. Okay, and each layer will be followed by normalization layer. So one-dimensional convolution layer will be followed by power normalization layer. When we are talking about power normalization layer, that means we are talking about amplitude should be less than or equal to 1 for all i's, for all signals. Similarly, estimated value of xi whole square should be less than or equal to 1. So these are the constraints, power constraints implemented during the implementation. That is the hardware constraints of the transmitter. Then coming to the channel, when we talk about the channel, we have implemented the Gaussian noise vector with zero mean and covariance matrix beta I. So beta will be equivalent to 2R EV by N naught all to the power of -1. So EV by N naught represents energy per bit. Okay, EB to noise power spectral density N naught. So using this, NR is the rate, beta rate. So using this, we will be training a model, and at the last stage, we will be using a softmax activation. Softmax activation is simply whatever the quantity that we are getting, it will be converting it into the probability. So it is simply e to the power of a divided by e to the power of a divided by summation of all e to the powers of a. I'm not going into the complete mathematics. So what it will be doing is, if we say this, so based on the signals, the symbols that we are getting, it has converted into normalized probabilities. And what we have to select is the maximum probability, and that will be, suppose we are using one hot vector here. We are using one hot vector here. So every bit will be represented by a 1 and all zeros, one hot vector. And based on this, a probability matrix, probability vector will be generated. And this probability vector, the maximum quantity will be selected. So if you can see, 1 was generated here, and similarly 0.85 was corresponding to the same vector position. So same variable position. So 0.85 here. So now S cap will be similar to what S is. So in this case, the error will be almost 0. Okay, so softmax will be doing this. So this will be just EA to the power of summation EA. Okay. So yes, so when we implement this and check the results, we have seen that the autoencoder result is matching the mathematical modeling. So because in this model, we were using the channel as the AWGN channel. So yes, the result was because we have not taken into any nonlinearity into account. This was a basic model. So yes, it was giving the results that was optimal because mathematical model was far sufficient to model the linear AWGN channel, and the trained system is performing as per our requirements. Fine. So yes, this was our first results, and now what we have started implementing and we have communicated is that rather than going for a single end-to-end system, now we are implementing cooperative protocols into that and checking whether that cooperative protocols are working according to our cooperative protocol-based deep learning system communication system is working according to the to the mathematical framework that was already available. Okay, and then we will be trying to, we have started trying to implement it in the underwater acoustic communication system, because for underwater acoustic communication system, their channels is not available. And acoustic signals are susceptible to multiple things, that the oceanic temperature, the bubble levels, then the blockages because of the marine life and so on. So rather than going for the mathematical model, we will be taking the data available by some oceanic institutions and training a model to get the desired channel estimation. Then just for giving a solution, so this is a paper by Emil Johnson and Eric Larson group. So what they have done is using the algorithmic approximation method. So this is maximization of some spectral efficiency maximization in massive MIMO systems. So the model that they have implemented is that the known algorithm was known. So MMSC algorithm was known. Okay. So the same data was passed through the known algorithm, and using that known algorithm, Y was generated. Now this Y, the output Y, the power requirement Y, will be used as a training data, training data for neural networks. So X is known, Y is known, and using this Y on X, the neural network will be training its weight. So now when the neural network will be trained, now we will be approximating the output Y for the testing data. So this system that they have considered N cell and 10 users or 5 users, whatever. So they have taken a massive MIMO with N cells. Okay. So the neural network, they have called it as a power network, PowerNet. Okay, so channel information X naught will be given, a channel information given. So weighted MMSC was taken to find out the transmit power. And then this was fed back to the power network, the neural network, the PowerNet neural network, to train its weight. And then P hat was calculated for the testing data. And when the results were seen, so here they have shown 3 results: the PowerNet, the joint pilot data power optimization, only data power optimization, and full power allotment. So if all the power is allotted to every carrier, then it is giving the least the worst result. Okay, so you can see that the sum spectral efficiency is the lowest for full power allotment to every data carriers. When we are going for this MMSC type, that is joint pilot as well as data power optimization, we can see that it is giving the best result, the red one. Okay, and the blue one is almost tracking that line. That means there is a very small error between the red one and the blue one. Okay. So now if we see this, then we can predict, we can see that the deep learning system is not giving that efficient solution. But what it is actually doing is that the time taken for MMSC was far more. So the weighted MMSC or JPDPO was taking almost 491 milliseconds. Okay, to compute this sum spectral efficiency. But for the PowerNet on the CPU it was taking 14.9 milliseconds. So where it was 491 nanoseconds, sorry, 491 milliseconds for JPDPO, it has reduced to 14.9 milliseconds in case of PowerNet. And this PowerNet was implemented on CPU. And when they have gone for GPUs and when they have gone for GPU, the timing was almost 0.0028 milliseconds. So the same function with a little negligible error was done in almost what we can say hundreds of times in less time. So for where 491 is there and 0.0028 millisecond is there. So we have optimized the timing requirements for performing such heavy algorithms. The complexity of MMSC is far high when we are going for massive MIMO type networks. So they have implemented and they have shown that deep learning based communication system provides a more provide a system that will be taking less time and energy resources as compared to the traditional algorithms that we were using till date. Okay, so this was the application. These are the references that was used and that can be studied for efficient applications of wireless communication, machine learning applications in wireless communication. So these are good resources. Anyone can read this. And when we talk about wireless communication, the data sets are not that easily available, but these are some IEEE is providing data for massive MIMOs, millimeter wave. So you can use the data sets from there. Then ComSoc is providing, that is IEEE ComSoc is providing, and some data sets are available here also. Okay, so UCI.edu is providing some data sets. Okay, so this is from my end. Anything you want to ask, please ask.
Dear participants, if you have any queries, you can ask now. Dear participants, any queries?
Hello, sir.
Yes.
Thank you. So here I would like to ask the data set, how it is generated or it is collected in order to work for deep learning?
The deep learning based communication system that we are working, we are generating random data. Okay, but because we are preparing the data itself, because X that can be simply random, right? Simply data can be generated. Okay, or random integers can be generated, and because we know X and we know Y, because whatever X is there, we want Y to be the same, right? Right. So now we will be training this data, we are preparing the synthetic data and training a system using that. Now, once the system has been trained, now what we will be doing, we will be preparing a different set of data. Okay. And now we will be seeing whether the output is matching our data or not. Okay. So for deep learning based communication system, we can prepare our data set on our own. Okay.
Okay, sir. Because actually for the networking layer domain working, sir, like traffic prediction and all, the data
for that
availability is very difficult, sir.
Yes. But now different researchers are sharing their data. So if you want, you can maybe we have some data available at our with us because we have asked certain researchers and they have provided us. So you can mail them directly and they are providing that.
Yes,
Okay,
sir.
so if
Yes.
you are working on network layer, you can directly ask the researchers that are working on that, and they are easily providing that. They are not refusing it. Okay, for us. So
Okay,
yes,
sir.
and IEEE is also providing the data. If you have the membership, lots and lots of data sets are available there.
Dear participants, any other queries? Any other queries regarding today's session?
Hello, sir.
Yes, yes.
Sir, first question is regarding the validation of all these results. Like, are we going to test it in some other platform for the validation of the whatever
Yes, yes. So
predictions we are
what
going
we are
to
doing
get?
is till now, the validation, that means you are saying that whether the result that is generated is acceptable or not, right?
Correct, sir.
Right. So what we are doing is we are comparing it with the mathematical framework that we have. Okay. So if we have a mathematical framework that is not accurate but it is approximate, and we were using that lots of decades, right? 2 or 3 decades from that. So if it is matching that's similarly for the last results that I was showing. Okay, so in that
Yes.
case, the machine learning based communication system was not giving the result as compared to MMSC, right? It was on the lower end. That means the sum spectral efficiency was lesser as compared to MMSC, but the time requirement was far less as compared to MMSC optimizer, right? MMSC estimator.
Correct.
So if you are going for a trade-off, if a certain error is tolerable for a lot of time saving, then we will definitely go for time saving, right? Because we will be trying to implement this in IoT devices. Okay, so and these
Correct.
IoT devices will be very low in power that is available at their ends. Okay. So
Yes.
that is why for till now, every researcher that is working on deep learning and RL, they are comparing it with the mathematical framework that is available.
Yes, sir. Thank you. Thank you so much, sir. Sir, I have one more
Yes.
question.
Yes, yes, yes.
Yes, sir. Like you said, the end-to-end optimization can be achieved here,
Yes, yes.
and individual optimization is
True.
required with respect to the existing systems.
Yes, yes.
But how do we ensure that? How do we ensure that? Like,
How do
do
we
we have any
ensure?
possibility of fine-tuning the parameters, or like before we could get
Okay,
the final
so
results?
when we are going for deep learning based communication system, okay, the
Mm,
system that we have
mm,
discussed, the end-to-end system in which multiple
mm,
layers were there. Okay, so
mm.
we have implemented Adam optimizer for that. Okay, we
Okay, okay.
are finally optimizing the weights based on the testing data, training data. Right.
Correct.
So the whatever
Yes.
solution we are getting, that is the optimal, and that can be more optimized if we are increasing the data set. Let's say I
Correct.
have
Correct.
tested it for 10,000 data. If I am making
Correct.
it 1 lakh, so it will be more and more
Correct.
optimized, right? So
Hello.
Like,
that's
is
yes,
it not
yes.
going to be affecting the timing,
Yes,
whatever that
yes,
you
that's why,
showed?
that's why. So everything has a trade-off. If I am spending
Yes.
more time testing, training the data, it will be giving
Correct.
us more optimal solution. But after a certain interval, it will be almost constant. So
Correct,
yes,
sir. Correct.
yes,
Hello.
yes, yes.
Sir, what is the difference between deep learning and machine learning? And how does it play an important role in communication?
So machine learning is deep learning is a subpart of machine learning. Okay, so machine learning consists of multiple things. Everything is inside that, right? RNN is there, CNN is there. So deep learning is a subpart only. So deep learning uh, for me, because I am not into complete machine learning, for me deep learning was a tool that was helping me, because CNN, the convolutional neural network that we were using, that was very easily trainable with the synthetic data that was available, and the models can be easily trainable and implemented for wireless communication system when we are working for 5Com, that is physical layer. Okay, so as a researcher, I am only working in physical layers, Okay, so yes, for me, deep learning is providing an efficient tool for optimizing my systems. Okay, as a, if you want me to answer what is the basic difference between machine learning and deep learning, I will not be completely giving you the answer, because for me, this is a subpart of machine learning. Fine.
Okay, sir. Okay. So, sir, may I ask one more question, sir?
Yes, yes,
So,
definitely.
deep learning application in OFDM.
Yes, it is there. Yes.
Orthogonal.
So,
Yes, sir. OFDM.
yes, yes, yes. So a paper is available for OFDM because same systems can be done, because once you have created a basic building blocks, right? Now what we want is just change the optimization, just change the algorithms. Suppose if I want to go for cognitive networks, right? So I know the basic algorithm how to implement a cognitive network, right? So now I will be changing my system accordingly. Whatever the power requirements, if now there will be two users, not a single user, primary user will be there and secondary user will be there, right? And there will be power constant, there will be interference constant. So I will be implementing that criteria into the system and making my system more and more tolerant to these algorithmic change. Fine. So if you are going for OFDM, yes, it is easily. So if you want, I can provide you a solution for that also. Give you a research paper for that, as well as discuss that offline. Okay.
Okay, right. Okay.
Okay.
Okay,
So
sir.
if you want, we can discuss it offline anytime.
Sir, can you show the slide number 31? Somebody is asking for data set resources. Yeah.
Yes.
Yeah. Dear participants, any other queries? Please fill the feedback.
Sir, please do share. Yes, ma'am. Sir, please
Yes,
do
ma'am.
share your mail ID so that for any queries we can contact you.
Okay, sure. It is with Pavitra ma'am, so if she can share it with you, or I will be sharing it with you all.
I'll put
Please,
it in
sir.
the chat.
Thank you, sir.
Just typing
Thank you
it in
so
the
much.
chat box. Okay, I'm just
Sir.
typing
Yes,
it on the chat
yes, sir.
box. Okay, so this is my email ID. You can contact me anytime. Fine. Anything else?
Yeah. Any other queries? Yeah, thank you, Akash sir, for accepting our invitation. So, and also for providing brief overview of this ML DL with respect to wireless communication. Thank you so much, sir. Sir, is it possible to share this PPTs with us? So that
Yes.
at the end I can share with the participants.
Yes, ma'am. I will be sharing it with you by the evening or tomorrow itself. Okay, I will be sharing it with you.
Okay, sir.
Okay. I will mail it to you, right? Or
Yeah.
should I mail it to you? Okay, fine.
You mail me, sir. At the end, I'll share with all other participants. Thank you very much for very
Thank you,
informative
ma'am,
session.
for invitation. Thank you for the invitation. Thanks a lot.
Yeah, thank you, sir.
Okay.
Thank you, Dr. Akash, from behalf of all the organizing committee for your time.
Thank you, sir, for this FDP and giving me